Hey everyone, so for this video, I'm going to be demoing how to do the data collection for the Conservation of Energy Lab. So once you've loaded the mathematical modeling, height versus velocity for a puck on a ramp, you're going to need to also have a spreadsheet where you're going to collect and calculate your data and make your graphs. Now, if we go into this, I'll full screen it and look at the kind of things we can measure. So we have the superconducting puck. This takes a while to buffer sometimes. But it slides, because it levitates, it slides down the frictionless ramp and hits it's stopped by the guy's hand at the end, but there's a portion where it's traveling horizontally. And because there's no friction and air resistance is minimal, for that last section, it's going to be moving at a constant speed, so we can measure its velocity. So we're going to need to measure the initial height and the final velocity. Now, one thing that's going to be important in our toolbox, you'll notice we've got a horizontal scale, a vertical scale, a timer, but then they also give us this line. The reason that's important is you notice the puck, because it's floating, doesn't start at a height of 0. But we can use this line to define 0. I'm going to put it in the middle of the puck like that, so that's measured from the puck's center of mass. And then if I go back to the beginning, I can move the scale, put the bottom of it down there at 0, at our 0 line, and look at where the height of the puck is. And once again, I want to measure the height based on the middle of the puck, based on its center of mass. So looking here, that's 25, 26. It's between 27 and 28, and it looks like it's between 26 and 27, and it looks like it's a nice 26.5 centimeters. So now you'll see why the way I'm choosing to do this in a sec. I'm going to put my height in this column, and that needs to be in meters, and I'll have my velocity, that's in meters per second over there. And my initial height is, we said 26.5, right? Yep, 26.5 centimeters. So divide by 100, that's 0.265 meters. And remember, you can't use units if you want this to plot correctly. That's why the units are up here on the column headers. Now, for velocity, if we go back to this, you can see right here, looks like about that frame, it's gone horizontal. So that's where I'm going to want to set up the start of my scale and 0 my timer, because I can use the velocity or I can use distance and time to find velocity or speed. So I'll let the timer run. Yeah, it hits his hand before it travels 15. So let's do close to 10. This is a little in between. We'll call that 10.3 centimeters. And whoops, one thing I forgot to mention, but where I start measuring position, I also need to make sure I zero my timer. So it travels 10.3 centimeters in 0.0458 seconds. So this is why I left those extra columns here. I can do time in seconds. I'm not going to plot these, but I can make sheets do the calculation for me. Time and distance in meters. So the time was 0.0458 seconds. The distance was 10.3 centimeters. So divide by 100, 0.103 meters. And then velocity is distance. So I click that cell, divided by time, click that cell, enter. So there's my velocity. Now I'm going to want to do this at multiple heights, at least 5, to get a good trend going. Here, that was at height K. Let me do height I. Let that load. One thing I'm going to want to check, depending upon the height off the ramp they release it from, our zero line may shift a tiny little bit. So yeah, this is taking a while to buffer. Come on, pivot, you can do it. Looks like over there you actually picked it up. I guess we'll just have to rewind it to the beginning and let it go, even if it's annoyingly slow, this website. At least it is here because we're having internet trouble again. Come on, you can do it. I believe in you. You can buffer like a pro. You got this. All right, so in this case, looks like, yeah, there was a consistent height. So we don't have to move our zero line to account for that. So if we rewind this back to the beginning, move that scale over. We've got here, that's 21, looks like 21.5 centimeters measured to the middle of the puck. So 0.215 meters. Now, the nice thing about, and to get my velocity, all right, looks like about there. That looks good. It's level. I'll put that, shift that over to the back, zero the timer, play. And it looks like it travels 10 centimeters in 0.05 seconds. So 0.05 seconds and 0.1 meters. And the nice thing is I can click that bottom right corner and drag down to copy that formula. And it does that calculation for me. And I'm going to want to do that for at least 5 different heights spaced out. So here's a table I prepared earlier, and I also put in a starting point of 0, 0. We don't have that measurement, but this will help make the trend show up much more clearly. That we know if we released it from a 0 height, it just wouldn't move. It would stay there if it was already on the flat surface. So it would have 0 velocity. But to insert a graph, highlight both of those, insert, chart. And if you do this right, everything should already be plotted correctly. Velocity on the vertical axis, height on the horizontal axis, velocity versus height. And we can see that's clearly not a linear relationship. Looks more like a square root curve or something like that. So it'll be up to y'all to figure out how you're going to linearize that and then use that data to calculate gravitational field. All right, so there you go. That's how you're going to work out this lab.